So hi everyone, welcome to this seminar. Today it's our great pleasure to have Tembine Hamidou, who has worked a lot on games and learning in games and Minfield games and so-called Minfield type games. So today he's going to tell us about Minfield type games and data-driven Minfield type games. So thank you very much for having accepted the invitation and for giving this talk. And the floor is yours. Thank you.
Thanks, Mathieu, for the introduction. Welcome, everyone. This is going to be an online meeting, so we used to do online meeting the last 2-3 years. So this is alternative option that's going on, and so the idea here is to present you some of the examples we have been doing. We have been trying to apply Minfield type games. So that's going to be, I will define what it is, to concrete problems. We have been collecting data since the COVID-19 stuff, traveling around, and that's difficult in the COVID-19 period, and collecting real data on the field, and then trying to, gather this data, analyze them, and structure some stuff, and transform it into what we call distributionally robustness, Minfield type game theory. And that's data-driven because we incorporated data into existing models or other new models. And I'll try to explain some of the examples here. So this is actually joint work with several people from several groups. So I will mention the contributors in some of the slides as we go. And we are building an international lab, game learning and game theory lab with other partners from different countries as well. So that's why you have this logo with different partners. So I will have 3 parts. The first part will be on learning, evolution, and games. And there I will be talking about single agent learning, and then multi-agent learning, and then some notions of speed up in deep learning. How is it connected to game theory? Is there any connection between deep learning and game theory? And then go to MFTG, was Minfield type game theory, and use the data into MFTG. So that will be the last part. So data-driven will be the last part. All right. So single agent is trying to learn the certain pair of functions. So this is the setup. On the left, you have a cognitive agent. And cognitive means that he has the capability to learn, to observe, to structure, to analyze. So that's what we mean by cognitive here. So the cognitive agent is going to choose an action and explore the action space. It means at the beginning, you don't know the action space. Progressively, you explore, you try. So you gather data on the action so that you learn the action space. And the action space here is finite. The big A is the action space, but it's not known by the agent. It's known by we as people who are modeling, but not by the agent. The agent explore all kind of trials, and the set of possibilities that we try is the big A. Now, each time you try, you get a feedback. And the feedback here is a function of the choice, and then a realization of the random variable, that's W. And here I add extra term that's going to be new and X. New is the distribution of A of W, sorry, and X is the distribution of A. And of course, by doing that, when I take the expected value, you'll see that it's not linear in new and it's not linear in X. That's what I'm trying to put here, and that's what you call Minfield type payoff. Means the payoff, the expected payoff is not necessarily linear with respect to the strategy. Means the distribution of the action, right? So that's the idea of this colored version. Now, if you remove these 2 terms here, it's a classical problem. Means that you have expected payoff of our team here of A and W without these terms, And for those, there are a lot of algorithms. And one of the algorithms here is the multi-arm bandit algorithm that's extremely popular in machine learning. And the second class of algorithm that we present is the fully distributed payoff and strategy learning algorithm. So payoff learning, we learn the expected payoff here, and strategy learning, we learn the optimal action or the optimal X. That's what we call payoff and strategy learning. And I will present some of the examples of this payoff and strategy learning. So that's inspired from the Bellman equations, Bellman optimality equations. And we will design the Bellman so that it's fully distributed, because the Bellman needs some standardized case, some of the situations. So this is the...
Sorry for the interruption. I think there is a question maybe by Thanos.
Yes. Just to make clear, W, like, you consider it as states, or like, is it something more, I don't know, different?
It's just so it's a random variable with a certain distribution nu. But W is a random, is the realize, here is denoting the realization, and its distribution is new.
Yes, but there is no interpretation as like states in the problem, or not?
Yeah, it could be the state for this one.
Okay.
In this case, it's just IID at this step, so I don't consider state here, not yet. Later on, it will be state.
Okay.
Here is just an IID thing. So this is the problem. Here you will understand. So I take expected value of that object here, and I just want to solve this problem. So it's just stationary, the steady state problem. There is no dynamic yet, right? So this is the, let's say, nature state, environment state, right? Nature state, not individual state yet. Nature state. And that's IID. It has the distribution nu, and A is the choice, and it has the distribution X. Right. So usually we don't incorporate nu and X here, because we take the classical expected value and it's linear in nu and X. But when you go to meaningful type problems, it's not necessarily linear. For example, if you consider variance of the reward, then you will have something nonlinear, right? Quadratic in X or in nu. So that's what we have in mind by considering this problem. So R as a function is not known to the agent. So you cannot go and compute the gradient and apply, okay, if there is any gradient. But you don't know the function, the structure of the function. The agent doesn't know the function. But we assume that the agent, we observe a number, a numerical value here, as I mentioned here. So the agent is able to see the output, the realized output, but not the function. And the goal is to design an algorithm such that the problem here is approached. I mean, you are close enough to the maximum, if there is any maximum. And for that, we'll assume something on X, the strategy space. This is going to be easy one, because we'll say it's simplex, because the action space is finite. So X is going to be the simplex on A. So that's going to be a compact, convex, nice one. So, and then for nu, well, second moment to be finite, I mean, very nice random variable. All right. So we want to design, we want to learn the expected payoff function here, and we want to learn the X that is optimal that solves this problem. So that's, sometimes we add some decline, because we don't want, when it's working, we don't want very slow algorithm that will give the answer after, 2-3 days, and it's not needed anymore. So we want really something that's very time sensitive. Means there is a decline, and you have to give some interesting answer before that decline, so that we can use it. So here is the algorithm that we propose. So the first line estimates the average payoff approximately, right? So depending on the mu, if mu is 1/t + 1, if mu t is 1 over t plus 1, is just the average of the observations, right? And x is just a kind of soft max. So we call this one, we call it the imitative learning, because you imitate the actions that are doing better in terms of R hat. R hat is the estimate here, right? So you combine strategy and payoff. So this is payoff learning, and the second one is strategy learning. So this is very simple algorithm, and it does good job in a lot of cases. So let's see where it does a good job. So assume that the reward function itself has a finite second moment. It's important, because if it's not finite, well, it's going to blow up in the expression, the group appears. And then that's the main assumption. And you have to design lambda and mu. And then you can show that actually the average here is going to be close enough to the maximum for finite set here, non-empty and finite. And for that we have to, so the sigma that the second moment that appears here, appearing here as well. And then you have a bound that depends on t and the cardinality of A, means the cardinality of the action space. Action space is finite. So if it's very large, you need to explore all those actions. So you can imagine that is going to be heavy, right? It's going to be a bound that's probably useless, because if action space, the number of action spaces is higher than t, for example, you don't have time to explore. So that's the type of thing you can understand. But as t gets very, very large, then you want to show that this k t a is going to converge to 0. And the bounds that are in the machine learning literature are the following. So they have bounds like 1 over square root of t. So this is a classical bound. It's related to the law of large number, because that's why the IID for W is important here. And you can improve it by the technique of the finite second moment here to get log of t divided by t. That's one of the most improved version. Log of t divided by t is the improved version of this term here. It goes back to 10 years ago. I mean, there have been a couple of improvement, but not in the bound. It's in terms of variance reduction. So there is sigma here. You can go and try to reduce the sigma, not the k part, but the sigma part. There has been a lot of work on that variance reduction part, and that's also related to input type gains, because minimizing the variance is part of input type control. All right. So that's the single agent case. And of course, you want to extend it to continuous action space and use estimation of gradient type of thing. And it works, but it requires more conditions. You need some monotonicity of the gradient, if there is any gradient, and convexity of the function, where in the finite case, you don't need convexity. So you will need other extra assumptions if you want to go to continuous action space. And it's not been extended to correlated state case, except for some specific class of problems. And so that's the improvement that are needed. Correlated noises and how to meet a line by adjusting the parameters and so on. So I will leave this as it is, because and move to the multi-agent case. So question, can we get the same results, same setup in the multi-agent case? Not single agent, but multi-agent. So that's the issue. The thing is, there are some things that are working in machine learning. You want to know if those are going to work when you go to games, 2-player games, or infinite number of player games, whatever, right? So that's the question, and it's not very obvious, because the way the algorithms are working, if they were IID or uncorrelated, if you go to something that is correlated, we expect that the correlation will play different roles and different behavior. So that's what's going to happen. First, I know that you are all familiar with games, but this is a definition on games again. Strategic form games as a set of decision makers, set of actions for each of the decision makers, and objective functions. So a certain, let's say, well, I don't say here it's finite or infinite, but it doesn't matter, right? So define a solution concept that satisfies the feasibility of the constraint. That's called constraint equilibrium, constraint Nash equilibrium, and it's that when it's satisfied this mutual optimization stuff. Okay, so that's the game definition. And for the multi-agent learning, we have been working with since well the last 10 years, and you can see some of the papers here have been rewarded in the application. So most of them show that actually it does not extend to games. Most of the machine learning results does not extend to games. You will see limit cycles, strange behaviors that are there. That's not like the single agent case. And these were, you know, that's a negative results at the beginning, but it turns out that it's positive because if it's not converging, it means that we have to come up with new algorithms, right? And make it convergent when it is possible, and what are the functions under which it's going to converge. All right. So this is the slide that's explaining why we need you know, new algorithm, right? So this is the rock, paper, scissors on the left. Well, actually the second one, the third one as well. This is the dynamic, the replicator type of dynamics, and this is the simulation. So from the simulation, simulation means you consider a large population, and they can be selected randomly, and they can have one of the three choices. Those are the actions, and they play. So it's pairwise selection. And then they play, and then you look at the outcome, and you put the outcome there. And that's all 3D here in the 3D two-dimensional simplex. And you see that actually the average trajectory of the blue is the data, the black is the average trajectory. So the average looks like it's converging, but when you zoom, it doesn't converge. You could see here that it's not really converging. And that's so you need second averaging if you want to enter it in the triangle here. It has a name. It's called Chaplet's triangle. Chaplet, who got the Nobel Prize for economics and game theory. So we have summarized all of this in this book that's on distributed strategic learning 10 years back. That was published in 2012. Yeah, so 2012 book. That has all these results that I mentioned, except the midfield type part, the blue part that I put there. All right, so can we go to continuous action space? So I mentioned one simple example, so which is this one here. That's actually the French Alps. So for those who are from the Alps area in France, so it looks like this. It depends where you get your camera and which angle, but you can have this view if you are in the Alp area, and different mountains and the highest, right? You want to find the maximum here, but you don't see it. Well, you have a certain limited visibility range. So if you run your algorithm, it might end up to this extremum or this or this or this. So there are multiple extrema that you might end up there. You might be trapped in one of these extrema, local extrema, right? Not necessarily maximum, local maximum, but also local minima and so on. So can we you know, cook an example where from the local extrema it will move and then go to another local extrema until it's find the global extrema? And if you find that, how do you know that it's the global and so on? So these are the type of problems, right? So it's non-convex, non-concave situations with local extrema. And one of the algorithms that people use for this is the swarm learning. Is also popular in machine learning as well. And we try to put now this into context of games. So it means each player does a swarm learning, and if you do that, what happens? And the algorithm is the following. You have the classical swarm learning, and we now add index I for each of the agents. agents observe their payoff. So this function here is just the output of the payoff plus a certain noise, and agent adjusts their parameter theta. Theta is just position and velocity of the agent. It's not it's a classical model. And then there is a part that's related to local best and global best. Local best means you take your own trajectory and you look at from all the measurement that you get, where do you get the best measurement till now, from the beginning to now. So that's local best. And global best is look at your own payoff, but also look at the payoff of the position of everything that you observe, means your neighborhood or every other person who communicate information with you. So that's the global best for you. Global, but it's still local. It's with the rest. It's with respect to the agent I. So that's it's global for I, but local because it's from I's perspective. And there are other parameters that are inside these matrices A and B, and these are parameters that are randomness and design parameters. So what is important is that there is epsilon here, and the convergence rate will be dependent on those epsilons. And here is the connection with dynamics. So this is going to be, in continuous time, it's going to be theta dot equal to the term here, and here is a difference inclusion. So because the local best is up to now, where are the positions where you get the best measurement. So this is a set in principle. It can be a set because these numbers can be identical for some positions. And when it is a set, you get inclusion instead of equation. You get inclusion, and that might create some problems. And we actually had a lot of uses with this because the theory, the stochastic approximation theory, is for convex set. The set that you have here should be convex. And here, when it's not convex, it's not easy for engineers that, okay, it's not convex, what should we do? So that's the thing. If you convexify, it does not necessarily solve the problem here. Look at the case of the mountain here. If you convexify this one and this, you might end up here, and there is no mountain there. See, so convexifying it is not necessarily a good idea here. So that's the issue. Although, since there are a finite number of elements here, as you go, you could do the convexification technique, but then selection will be one at a time, right? And then you get these results here. So it's in the order of epsilon, square root of epsilon, similar as the previous results on T, right? So this means if you cook the epsilon well and the parameters, it's not very bad trend, although you still have the convexity issues. We have applied it in the context of energy with 2 power stations just to see if it's working. And the constraints are, the production constraint, and the reward is production, that's supply, times price. So price is a function of demand and supply. And then there is a production cost that's linear in production units for power station 1 and power station 2. So it is a relatively simple example. And we have tested this in South Italy, in Sicily, because there we have the power stations, the solar panels, and so on. We get the data to see the price increasing or decreasing depending on the supply and the season as well. And the idea is to find the equilibrium. So the 2 colors, the blue one is for power station, the producer 1, and the red one is for producer 2. You run the swarm learning, and these are around the Nash equilibrium. The particles are around the Nash equilibrium. That's the swarm for player 1 and swarm for player 2. Right. So they don't converge. The reason is there is a range of epsilon, and so they keep moving around. But they are clustered. So initially it was like this here, right? Uniformly sampled the action space, and then finally it's clustered around the equilibrium. So it's not that bad, right? So that's what we get. And then we said, okay, can we find the best equilibrium and look at the basic example. So this is an example where you have it's called anti-coordination games with the noise, and you don't have the distribution of the noise. So as an agent, right? But you can observe the output each time you experiment, right? So there is a global optimum. It could be this one or this one when you take the expected value, because the expected value of this part is 0. And you want to find the global optimum using this distributed learning algorithm, and that's what we have done. It is called random matrix games because you could see here random matrices, and that's actually what awarded a couple of years ago, 10 years ago. So let me summarize. For some class of dynamic IID situation, even in games, you can still do some things like simple games with specific structure, like potential structure, or very basic ones. You can trick, and if you want, there are a lot of algorithms that have been designed for game theory as well. And well, it doesn't work for complicated games like replicator games. These are two-player games, but still it doesn't work for those cases. It means it doesn't find the Nash equilibrium. But still, there are some things that you could do. You could break the limit cycles if there is a limit cycle and so on. So that's the type of thing that I was presenting earlier. And for state-dependent case, there is a Q-learning algorithm, extensions of Q-learning, all bunch of extensions that have been done in the literature. And we have been doing this co-DPAS. So this one is fully distributed payoff and strategy learning is the one that has been developed by our group. And it does apply to, where the Q-learning apply as well. So I will present some of them in the Q-learning case. So here is an example of the pursuit, co-DPAS, and the imitative. So the imitative is similar to the one that you have seen earlier. The only difference is that here I averaged by the number of trial on L. L is an action. You have been trying L a certain number of times, and this is the counter. This is the count. Theta L is the counter for how many times you have used L. This indicator function is 0 or 1, right? So, and that theta L appears here. Let's say initially that theta is initialized to 1, because otherwise you might have a problem with the denominator here, right? So then each time you update this component only when there is a trial, and then it will be initialized, right? Because here it doesn't update the component if there is no trial as. So that's fine. And then the distribution of X is updated using the estimate that is here, and the lambda is the design parameter. So each player J does this algorithm. That's imitative, and the one on the top is similar. Instead of doing the entire distribution that is here, it takes the best estimates across all the components. So that's kind of best response, but estimated best response on the estimated values. So if the estimates are correct, it's going to be something similar to best response, but it's a kind of averaged out. So you don't take the best response directly, you average it out with the previous. So there is a kind of averaging structure that compensates. And so these are the first one is very fast, is pursuit pretty fast. The second one is immediately much more slower. So it depends on the games. For some games, the first is fast, but it might crash, it doesn't work. But the second one, it might work, but then slow, right? So that depends on how you design your parameters. So we have shown that in this example, the pursuit one is fast in the sense that it's faster than classical ones, the one by Bush and Monster, and the fictitious play that's react to the empirical play of the other agent. Here you don't see the other agent, but if you assume that you see it, you can book fictitious play, and this pursuit code is much faster than fictitious play. And you could see from the equation why it becomes faster. It's because of this component here. Best response, when it works, is much faster. And the entire algorithm as a geometric law is convergence to in the basic 2x2 game. So it says a convergence to the global optimum with the geometric law. It's exponential convergence, right? So this is nice. And globally, so this is the type of result that we were able to prove for this particular example with the 2x2. If you denote by GO, so that's global, the maximizers of all the payoffs, that for any precision that's given epsilon, and then any delta, you could cook a time. You could cook T star and cook lambda such that the convergence to after a certain number of points, the distance between where you are and one of the global optimum is less than epsilon. It's just one of the global. We cannot select in advance which global. That's an issue. But because when you have a stochastic algorithm, it's not, you know, it's not easy to fix in advance which equilibrium or which global optimum in advance. But the distance to the global optimum is small. I mean, in probability, because the probability is higher than this number here, 1 minus delta. So that's convergence to global optimum in probability. Can we extend to the Binfield case? That's the question I was trying to answer the last 6 or 7 years, and we were able to do only for specific cases. And let's start with the filtering problem. So you have a distribution that you don't know, and you have observation, and from the observation you want to infer and estimate the next distribution, and at some point you want to estimate the system state distribution. So these are summarized in these operators. Sn means sampling phase. P is for prediction. It could be an update, Bayesian update, or any other. D is for space decomposition, because in the application here we have to decompose the area, the domain, the constraint, and so on. So that's for decomposition. And C is for correction. So sometimes you predict and then you correct, right? If you do a Bayesian update to satisfy the constraint, you have to do some averaging so that the constraints are met and so on. So there should be some correction term, and that's prediction correction is part of it, but decomposition as well. So this is the flow chart for the Binfield type filter, and this here is a basic example. So system state is this example here. Binfield type because of the term, the color, the blue one here, second moment, let's say, and the observation is given by here. So you observe x squared roughly. Assume that beta and alpha are small. Okay, so it's like instead of observing x, you are observing x squared. Okay, you could see it in this example. So when you observe x squared, you observe only the positive part. I mean, you see only positive numbers, but x could be on the other branch, the negative side here, right? So this is like x, this is y, and from y, you want to guess what is x, right? Okay, so we run the algorithms. Binfield type filter, particle filter, and then we have an improved version of the Binfield particle filter, and we have PSO, means particle swarm filter, and then we have the state trajectory. So the state trajectory is going here, and then one of the algorithm particle filter is going on the other side, and then particle swarm learning, it's going first on the good branch and then deviate and coming back. You see, so it's not that easy to track this type of system. That's why we consider this system, because most of the filtering algorithm fail for this system, for this example. And you could see here that the Binfield filter does a good job. And there's an illustrative example, but it tells you why we need new filters for Markine-Vlasov type of system, and this is Markine-Vlasov type. And we have done, you know, more estimations and the errors, mean square error, the global one for the entire domain in 3D, and I will give you an example of it. So this is the 3D example. The algorithm is identical, but then it's applied really in three-dimensional object. Let me show the movie somewhere here. I think it's going to work. Okay. If everyone sees my screen, okay, no, that's the wrong one. That was actually the mountain example, so to show that it was working. So this is you have two aircraft, so going different directions, you have to track their position, and this is the tracker, the particle that you see. So the particle is really tracking the position for both of them. Approximately, you could see here that is tracking approximately the position. All the swarm are following the aircraft. So this is the area, this is C area where you have no measurement and so on. So still it's doing some good job. So that's just an illustrated example to show you. Okay. So the mean field filter is doing the best job among the ensemble Kalman filter, the particle filter, and the particle swarm optimization. And you can find the details of this in the mean field filter paper at SIAM on Scientific Opinion. All right, so that's for the filtering part. So we applied to traffic data, that's the real data. And we had the camera data for several semesters. And then we try to track the position of the vehicles depending on the camera output, right? So you have vehicles and you want to identify the vehicles and then follow them, estimate their position when they go under a tunnel, for example. So that's the type of thing we have been doing for several years as well. And I'll show you the example in Switzerland that was done for this. Where you want to guess the position, but also the congestion. So that's what you get. On the left, you have the Codibus algorithm. On the right, you have the ground truth, and you want to see if the learning is some kind of can we reproduce what is observed or not. And well, they are not really similar, but the portion where there is congestion are relatively similar. So that's the idea. You don't have the same number of vehicles, of course, but you have similar congestion users. So this means we'll be able to predict the congestion areas and when it's going to happen. And then you can do suggestion for extension of new infrastructure or what should be the infrastructure and so on. So that's the type of thing where you could apply. Another example is the evacuation of the Burj Khalifa in Dubai, and that was in collaboration with Samsung. So Samsung constructed the building, and they have done, the evacuation plan, very nice plans actually. And we reached them and we said, okay, these are the evacuation floors. Every 25 floor, you have an evacuation area, and then when there is an alert, so you might have the mall plus the tower, you might have 50,000 people. And this is, of course, large number, 50,000 people. So you could do some estimates, see the number of people on each floor from the camera or just from the estimation of the hotel, and then do some evacuation plan. The problem is that you use a lot of floors to come to this area, up or down, depending on your floor. And we have been trying to do some benefit type counting measure. You count how many people are around a person and so on. So this is detailed in this paper, multi-level building evacuation. And this is the floor details, for example. And these are exit areas for the ground, or we could take a stair to go down. All right, so many other examples are in this paper. It's a survey on all the applications we've been doing in engineering, although most of them. Let me move to the deep learning part and why it's connected to games. So on the left, you have game terminology. On the right, you have deep learning terminologies. So a player I mean, a decision maker is somebody who adjusts something. So you could assimilate to the neural unit. That's a unit that does this type of operation here, and then objective action is going to be the weight. So the action that is taking is this weight, and the objective function. Well, that's objective function is the final output. That's loss function. So that's same for both. A game might have multiple objectives, right? You can have a sub goal, you can have a Pareto objective, you can have an individual objective, you can have a equilibrium selection objective. So that might be related to what we call feature. So that specific feature in deep learning might be a goal specific constraint or in games. Measurement is measurement for both output or any type of measurement, right? We design games, means we design payoff functions such that it does specific job, right? And in deep learning, we design architectures as well, right? So every agent is going to design its architecture. So there are some terminologies that are similar, and you could do, if you are a fan of this type of composite functions, saturation functions, and the weights, you might do it with billions of parameters like this and continue on this. So you optimize it and you might approximate your specific problems. And we have been doing this for specific problems in traffic network, and we have been doing, for example, acceleration of deep learning and in the context of type filters for big data and so on. So these are all available online. The closest example is this one, distributionally robust optimization, because when you have this big data and distributions, you might want to look at the worst case from the data perspective and so on, and that's what I will present next. Let me briefly recall the results. The first results is about the gradient, and since everyone is familiar with it, I will just skip it, right? It's just a bound like this, log of t divided by t, okay? Just remember that one, log of t divided by t, that's their bound. And we look at that and we say, let's accelerate it. And we propose this algorithm here that's based on Bregman divergence. And that's for G is the convex function. And then define a Bregman divergence like this. And this M is the main field. I mean, in this case, it's just a vector on RV, let's say a vector on RD, okay? You adjust this way. And if L is convex, you can show this type of bound. Okay? Just convexity, sorry, strict convexity for L. So the difference between the mean field and the solution is bounded by this type of term where beta is a design parameter. So you can say that this is like average exponential convergence, right, which is nice. And you could cook the design parameters, alpha and beta and so on. So you might get exponential convergence, you might have a double exponential, triple. It depends on you. You could go as far as the machine can allow you to go. You can have also smaller scales like polynomial order, right? So this is the advantage of this Bregman learning. But of course, if you want to go here, your machine will be quickly limited. But if you are in this range, you can do maybe more things. And if not, you stay here, right? Instead of 1 over t, you have 1 over t squared, for example. So that's the interesting part of it. And we have applied this to ImageNet. So this is extremely popular in deep learning for classifications, recognitions, and so on. And these are, we have applied it for art as well. From your top artist to a photograph, you can do your deep learning and see regenerate. So this is for generation models. And this is the one on the right are generated, the one on the left are, the initial inputs, and you can improve with image quality and so on. I will skip this part because I see that the time is running, and I'm still Okay, let me present the game theory component. So I introduced this code. This is the uncertainty set. Among all the distributions, what are the divergence that are less than rho? Rho is given. So this is a ball, but in terms of distribution. So if the divergence is it could be a distance, but it's not necessarily a distance. If it's we have been working with Weissenstein distance, T to be the Weissenstein, but after that we consider classical divergence. So we have done F divergence, Brakman divergence, and so on. So while we do this, I will explain you here. So consider now multiple agents. So we are going to do multiple deep learning. Each agent is going to run its own deep learning, which is going to be a type of adversarial deep learning for each agent. And then the agent has a certain loss function, and this is the type of problem we want to solve. Take the parameter, so Wi, omega I is now denoted by AI, and then worst case distribution among the uncertainty set, and then optimize the expected one. Right, so this is what we call distributionally robust gains, distributional robustness in the M is coming from data. That's the link with data driven, but the data distribution is not the exact distribution, because data is just collected and you might consider empirical measure of the data, and then try to make it continuous, smooth, nice distribution from there, and that's will be M. So M is not the real distribution, and you are trying to find the worst case distribution around M. So that's the idea. So you consider your data, but don't trust the data as if it was the exact distribution. So then we need another theory. Instead of duality theory, we need triality theory, because there are three terms: infimum, supremum, infimum. So you have this type of inequality. Using duality theory, you have this type of inequality. And if you have supremum, infimum, supremum, you can have also duality theory to get this inequality for. And we have used that actually to show that the upper and the lower are the same. So these are all identical and so on. For specific examples, of course. And the divergence, the F divergence, defined this way for a function F. And when F is X log of X, you get the KL divergence, the Kullback-Leibler divergence, which is extremely popular. But there is a unity continuity of the measures here, of course, which I didn't add in the slide. But for those who are familiar with it, you need to do this type of thing. You need continuity of emitting with the measure acting with respect to M. So the ball is redefined here. And then the triology theory transform the problem into this form here. This is just Lagrange multipliers of the constraint that are here are added. So you get the F sub M, then we use triology theory to transform the problem, and then the F sub F becomes just F, one symbol F with the parameters. Okay, and the parameters are easy ones. Lambda is a real number, mu is another real number, and then we optimize HI. HI is here. There is a differential duality for F. F is just a converse function, and I is the cost function. All right, so now we can optimize this, and for that we use a Brakman algorithm. So this is the Brakman algorithm. G is a chosen convex function. Alpha and beta are design parameters. HI is the function that is above here. That's HI, and that's it. The random variables here are W is coming from observation. So you run this d over dt, because x is a function of time, alpha is a function of time, v is velocity, function of time as well. So you run this. This is going to be improved version of the gradient, much faster than the gradient. The convergence is the one that I've shown you. And with that, you apply to deep learning and see the nice results that are here. We have compared with the state of the art, and this was awarded as well as the fastest at that time when it was published. All right, so let's move to meaningful type, where now the dynamic version, and I have the classical references here. You know, the basic references, the foundations. I used to say that meaningful games were there before, but without the without the name meaningful games, right? So in the discrete time, for example, you can look at the paper by Ivanovich that's established the optimality equation, means Bellman equation and Kolmogorov equation together. That goes back to the 80s, and the continuous time more recently, right? So, but meaningful type game is, as I explained earlier, the payoff function at the expected payoff is not necessarily linear with respect to the distribution of own states, right? Which in meaningful games it's linear because the main field, you don't contribute as an individual to the population main field, so the expected cost is linear in your own distribution in meaningful games. But in meaningful type games, it's not necessarily the case. That's the main issue. And then so that's to illustrate that, we say consider a function, the instant payoff, to be a function of state action and the distribution of state or action. So that's the meaningful type. There are other advantages in the meaningful type, well, with complications maybe as well. So you don't have the indistinguishability anymore per class, at least not imposed. If it is the case, it's nice, but it's not necessarily imposed. We do this for applications, and it turns out that it's important to drop this assumption in some examples. And the literature here goes back to 2011. So meaningful type control by Boalem, Geish, and his co-authors. So that's, you see, 2011. So these are control parts, meaningful type control, and Mathieu is online. So that's 2014. See, 2014. So meaningful type control, controlling the Markin-Vlasov type of equations. And we extend to meaningful type games. So that 2014 here at IFAC World Congress, meaningful type games for the first time, and then a lot of extensions, right? And different methods: maximum principle, dynamic programming, direct method, and other methods, type of Wiener-Chaos extensions, and the other methods as well. So the key thing is the variance reduction, because that's the easiest example, and then progressively you put the entire distribution. So let's look at the variance reduction. These are two states. On the left, you have the average dynamics. On the right, you have the state dynamics itself. You see that the variance are not similar. Although the mean are not similar, but the mean are relatively close enough. We see what they are doing. This is about temperature control. And the variance are, so the blue one is not doing well in terms of variance. So if you are working on sensitive temperature applications like healthcare at the hospital, you might not want big variations in terms of dynamics trajectory, right? So here is a variance aware example. The red part here is related to the part that is new. I mean new, the mean square. So because of that, you are not linear in mu. This is the part that's linear in mu. So that's the second moment, but this part makes it of meaningful type. And the state here is the diffusion. I mean, this is the divergence term here. You have a Laplace term here, and you want to solve this problem. And you can solve it manually. I mean, without any difficulty. You might need some potential transformations, but we solve this explicitly. And the solution, if you want to solve with Bellman, you can also solve it. And the solution is here. The optimal control is given here, and the optimal cost is also explicit here. So this is the optimal cost. And you have to identify alpha, beta are here. And you can even go further. Alpha, beta are detailed here, explicit this time. You're going to do better than that. And the optimal cost is explicit, right? So these are solvable things. So can we go to games? Because these were not games. So to gains, so let's say each player has its own sensitivity parameter with respect to the variance. So this is my variance sensitivity, the variance sensitivity of I, and then you have an infinite type gains. So the dynamic is similar, but so dependent now on the choice AI, right? 2 players we consider, and you can add even some planning type of constraints. So you can say that I don't want the variance to exceed a certain number at time t1. I don't want the mean. I want the mean to be equal to a specific pre-cooked mean, right? Even with those constraints, you could solve. And this is the Bellman system of Bellman equation. And the solution is also explicit that you could find in the paper. Okay, so we could extend to nonlinear case. This is the quadratic case that we solve. Nonlinear and maybe not quadratic, depends on the case. So these are the category of problems that we were able to solve, even when it is not quadratic, right? Nonlinear or non-quadratic. So you have trigonometric functions, you have quadratic dynamics, and your polynomial or power law type of thing with variance theory, power law. You have hyperbolic functions. So all bunch of classes that have been solved. And the data-driven part is to say that now you estimate this coefficient through the data. I have 2-3 minutes on this, and I'm still already late. So let me go to the application to COVID-19 to see how we incorporate it, right? So 2-3 minutes. The dynamics is dependent on location and then position of the agent, and then COVID status, and then the past. The past means that comorbidities of the agent and time, right? So we consider this type of dynamics. You see is for age, sorry. And this is the global dynamics that you consider, but the parameters has to be estimated from data. And for COVID-19, data is available, and some data are publicly available, and you can consider those to test your method. And when you do that, you get the transition parameters. So parameters are obtained from the data, and then you plug those parameters into your model in the previous dynamics. So that's why it's data-driven dynamics. And then you, on top of it, you build your meaningful type thing. So each time you have a new data, the dynamics changes because the parameter have changed, and then applied. So data are from the Google data, telecom data, the map data, all the institutions that are giving data are involved, and apply it to some optimization for 3 categories of agents: optimization for the individuals, optimization for the companies, and optimization for the institutions. And we compare to other techniques. So other type of algorithm that track the data. These are some other techniques like SIR and so on, or the time series algorithms. So we list them and we compare with that what they do, and we can make it. So the cost function is the error here. The global cost function for the algorithm is the error. So this is the RMSE global one, and you look at the RMSE for each country for the time horizon, the estimated one they realized after 1 week or 1 day or 1 semester. You could check all your predictions and so on. We have been doing this for 1.5 years, and then divide it by the horizon, because you need to normalize, divided by the number of components in the data here. So data here is tested, positively recovered, deaf, and vaccinated. And the time horizon is different from one country to another because the propagation of the virus were different from one country to another, at least the time slot. And divide by the number of countries. We have considered 210 countries. All right, so with that, we have done a lot of, error comparisons, and you could find them online. That's it. So let me summarize. We take data, we estimate parameters from those data, we plug that in the models, and then we run meaningful type gains. Thank you.
Well, thank you very much for the presentation. Very nice presentation, Hamidou. Thank you. Are there questions, comments from the audience? I have one quick question on the calibration part. So the way you calibrate is by producing the aggregate quantities, like for example, number of infected people, number of deaths, etc. And you compare with the true numbers, and then you go back and tune the parameters in your model and fit in this way.
Yes.
This is correct?
Yeah.
Okay.
So the problem with that is it means that you are trusting the data. But the thing is, with COVID-19, it's really difficult to trust any data that is published. So you might say that this is just a training for the algorithm, and when you have the real data that you could trust, then how it's going to behave and so on. But for COVID, I agree, it's not really a good idea to consider them as what is going on. You might have under-reporting, and sometimes in some countries over-reporting as well, depending on the funding that is coming. We have been dealing with all of that. But so we consider data as aggregated because they give the aggregated. They give, for example, number of infection of a country, which is the sum of other things. So they give as aggregated.
Yes, typically you don't get data for the individuals, you get data for the population. So
right. So that's why we do the integration, and as the object, we integrate over space typically, right? We cluster on that. Yeah.
Okay, sounds good. Thank you.
Thanks.
Any other questions or? Okay. Otherwise, well, thank you again for the nice presentation.
Thank you.
See you.